You think it's okay? All right, all right. Okay, this is an opportunity to talk on a short notice because I had given this talk, or actually not the same talk, but the same slides a few months ago at a conference on high-speed computing in Oregon. So since this is the work I've been doing, so I think it's also good to sometimes share with all of you what I mean by high-dimensional computing and where it might eventually end up. So first of all, you might ask, why high dimensionality? And we can look at the computing resources that there are in the brain, and then just sort of reflect on how the brain work can sort of be understood in computing terms. The number of neurons, about 40 billion. Number of synapses, 240 trillion. And these figures, they're some sort of ballpark figures, but they are big enough to be impressive.
This is the cortex.
Excuse me?
This is the cortex.
I think these numbers are for the cortex, but for cerebellum and cerebrum cortex. I mean, that's probably where most of the synapses are anyway. So if you assume that there is a synapse is worth a single bit, that translates into 30 terabytes. I mean, we are very comfortable with megabytes and gigabytes and terabytes because some disks, I believe computer disks now are terabyte. Well, 30 terabytes, it translates into 30 million books, or if you think of a 100-year lifetime, that would be 800 books per day for 100 years. Or if you think in terms of information rate, it would, if you're storing that much information, you would be storing 76,000 bits per second for 100 years. So that is an impressive number. Somehow the brains are prepared to deal with information at these scales and at these numbers. And then if you look at the fan-ins and fan-outs, in some neurons, up to like 200,000 neurons either coming in or synapses coming in or going out. And on the average, about 6,000 synapses per neuron. And if there are 6,000 going in, then on the other side, they also mean there has to be 6,000 going out. So those are sort of the figures that determine or give an idea of the size of the circuits and the size of the vectors. If you're thinking of these things in terms of vectors, it would be 6,000, 10,000, 100,000 dimensional vectors. So there are some principles of architecture that such numbers imply. First of all, large circuits. It means that we should be computing with high-dimensional vectors, for instance, with 10,000-bit words rather than with 64-bit words. And that means there would be 30 terabytes would translate into 64 billion of these 10,000-bit words. So those are the numbers to actually appreciate in terms of the computing architecture. The circuits can be very large, and then also a massive memory, because large amount of information is learned very fast and retained over a lifetime. This also means that the learning of new information may not destroy much of what's already there. The learning has to be minimally invasive. And the conclusion that I would draw from that that the encoding of information and the memory storage, they have to be separate processes. Now, if you look at neural nets the way we have been working with them for several decades, in most neural nets, in most deep learning nets, the encoding and the storage, they are entangled with each other. And one of the terms that you read in literature is that there can be something like catastrophic forgetting, and that is when you have to produce new codes that also involve the memory in a very intimate way, then the new codes will disrupt what has already been stored. So having separate, just like in an ordinary computer, you have memory that in some sense is separate from the operations that deal with the numbers, your addition and multiplication. So you have operations, you take some information, you operate them, and you can store in memory. That's standard practice in computing, and I suggest that it something like that should also be accepted as being rather standard in brain-like computing. So massive memory. Another thing is that we should be able to use randomness in a constructive way. And if you think of ordinary computing, well, you don't want the components to be random. You really guard against the components being random, but also randomness is also then used only as sort of an algorithmic, like in Monte Carlo methods. You can use randomness, but you create that randomness with deterministic components.
There's a question, Pentti.
Hmm?
So, if I understand, isn't the number of possible information size is like 4 to the 3 billion? I'm just understanding, why don't you think 4 to the 3 billion is enough to specify synapses?
For
Am I doing that wrong? You see what I'm saying, right? 4 is the number of bases, so...
yeah, base pairs.
4 to 3 billion possible configurations of things you can make with that.
Yeah, well, I just...
240 billion possible configurations.
The num-
Where's 4 coming from?
well, it's,
4 base pairs.
the number... Okay, here I'm just throwing...
Each base pair was a synapse.
Here I'm just drawing about the...
It doesn't have to match, it doesn't have the same number.
No, that's
That's how you...
that's true. Yeah, this is. I wouldn't say that this is a
I mean,
proof of
it
anything.
doesn't code for every possible synapse that can occur, right?
Yeah.
You know what I'm saying? So that's what
Well,
that
that's
was.
what he's saying.
That's what you're saying.
Oh.
Well, that's what he's saying.
That's the point. It doesn't.
That,
Right, but I'm saying, like, why does random... I guess I'm confused as why random is... Why is it random?
okay, so this slide I need to work on. Okay. Any further on, we'll use randomness in other ways. But here I was trying to argue that to wire the brain, the information that's available in a genome is not would not be suggesting that the information in a genome is not sufficient to determine the brain in minute detail.
Well, assuming that you can produce all possible variations of brains, right?
Yeah, and so there's enough information to provide a general plan of how to wire a brain, and then the rest can happen somewhat randomly, and the system still can work fine. And this is not how engineers built when they design circuits. This is not how.
Well, I guess a good example maybe you should point to is the retina configuration of the hexagonal lattice is not perfect.
Yeah.
Right, so there's some randomness in how that's arranged, which means you don't have to store that information. That kind of thing you're talking about? Like when you see cones, right, or whatever.
Yeah.
Like it's not perfect hexagonal. lattice. It involves range.
Yeah. In fact, if it were perfectly hexagonal, you would get these Moray effects. There's actually there's something positive to be said about the retina being perfect grid.
What's the Moray effect?
Anyway, we in oh did you?
If it were a perfect hexagonal, it would be bad thing. Is that?
I think you would get like alias.
Yeah, you get these Moray patterns.
Oh, okay. All right.
Yeah, and by having randomness, you avoid that kind of thing. Anyway, in these models, I use randomness. I use representation that benefits from randomness. And another thing is that with brains, we can get reliable computing with unreliable components, and when performance degrades, it degrades gradually. And this is sort of as opposed to catastrophic forgetting. Is that you're doing fine, you train a little bit more, and all of a sudden you go through a phase transition, and all bets are off. And so graceful degradation is one of the things that we want to get from neural nets, we want to get from our high-dimensional computing model. And this speaks for having information distributed, using representation that distributes information in what could be said is a holographic or holistic manner.
Can I add something to that? I think this is actually overlooked in just like semiconductor design and like computing in general, to like actually make a system that is like this, is like truly distributed in its function, and they can still perform like complex computational tasks.
Well, that's what we're here for.
Yeah.
To go through the exercise of how you might compute with under these constraints, and then suggest to engineers that well, we can get this kind of performance with these kinds of systems. You may be interested in building hardware that matches. I missed that.
I said plants, probably like vegetative plants.
Yeah.
We had a journal club on plants.
Okay. And the thing is that these principles, the four principles, they can be realized in a fully general system of computing. Is it computing that's as general as the computer that's on your desk or on your laptop? In other words, there's no using these principles doesn't really end up with any restrictions in the tasks that are computable. Well, if you think of something like a Turing machine, Turing machine really doesn't have very complicated structure, and yet it also can be a universal computer. That's a theoretical result. This general computing that I will talk about, it resembles traditional computing with numbers, but it also works with components that can fail, and it also resembles artificial neural nets, but it avoids high-dimensional gradient descent or backpropagation. And this I think is an important thing that is also related to what I referred to previously as catastrophic forgetting, or the entanglement of representation with storage. So we hope to have something that is just as good as old computers and just as good as neural nets, but avoid some of the restrictions or some of the limits that those traditional architectures provide. And so now let's go a little bit into the detail of how you might compute with 10,000-bit words as opposed to computing with 64-bit words. That's now, I guess, the the most common way of computing in our computers. And so first let's look at, for reference, let's look at just ordinary computing with 64-bit words. So what do our computers have? They have an arithmetic logic unit. And this arithmetic logic unit, it's a special kind of wiring that allows certain very important operations to be performed very efficiently on these 64-bit words. And the most important of these are that you can add numbers, and you can multiply numbers, and you can compare numbers. You can also have operations for fiddling with bits and shifting and rotating. But we can just concentrate on these two operations, add and multiply, and then having a method of comparing numbers, sorting them, or comparing for similarity. And then there's this random access memory, RAM, and that one is for storing numbers, it's for storing pointers, and it's for storing the program code, which is some sort of mixture of numbers and pointers and indicators. So that's what we are all familiar with and have dealt with over, well, however long we have been computing in the current computing paradigm. Now, how about computing with 10,000-bit words instead of 64? So the important thing here is to realize that there are similar operations to what we do with numbers, but now we are dealing with vectors. And so we need an operation for adding of vectors, and we need an operation for multiplying vectors, and we need an operation for comparing vectors. And it turns out that when you're dealing with vectors, you get one more operation that turns out to be very useful, and that is you can permute the coordinates of the vector. And each of these operations, if you're dealing with binary words, 10,000-bit words, we can use an addition operator that is really just the thresholded sum of the vectors that go into the sum. For multiplying, it's this important thing here to notice. If you're dealing with linear algebra, usually you say multiplication of vectors produces a matrix, or it produces a scalar. Here, the multiplication operator, it's very important to realize, what corresponds to the multiplication operator, it produces a vector of the same dimensionality as what you start with. And for binary, it turns out the exclusive OR, where you call coordinate-wise exclusive OR, it is a very appropriate multiplication operator. And permuting means that the simplest kind of permuting is you just rotate a vector. And for comparing vectors for similarity, you can use, in binary, you can use Hamming distance. With real vectors, you can use the cosine. Some form of scalar product is usually behind the comparison of vectors. So you can, how similar or how different they are.
So Pentti, I guess a question about the permute operator. So when these are binary vectors, then the operator R, I guess maybe what I'm asking is, like, the more general way of formulating that is R as a matrix. Right?
Well,
Matrix times.
if permutation, yes, permutation can be thought of as a matrix times the vector, and the permutation matrix is just yeah.
And like the row, I mean, here is just like row permuting by one, but you can also think of this as circular convolving A with 0, 1, 0, 0, 0. So that's like, but you could like more generally describe permutation as circular convolution, where you can take any two random vectors and combine them.
Mm-hmm.
But here, just this kind of permutation is just like circular convolution with a particular vector that rotates one.
I will have something more to say about this nature of these operations further down, but it is true that the permutation is a form of multiplying by matrix.
Because it just, I'm just thinking in my head, you know, well, let's see, I mean, like, if you just grew up on linear algebra, you can't imagine anything else but that.
Yeah.
It's sort of, you know, this is a different system, and then I'm trying to sort of recast it as things we know in terms of linear algebra. It seems like you can, in the sense of like, if you think of that permutation as like a matrix multiplied, right? P is some matrix times A.
Yeah.
So, and that's a rotation matrix, right? And then the other multiply operator is, you know, A times B. So you could think of that as like that's equivalent to like multiplying a diagonal matrix
Yeah.
by the vector.
Yes. Yes. Yes.
And then in linear algebra, like any matrix can be rewritten as a rotation and a scalar rotation, right? So maybe, like, that's what I'm trying to think of. So we could sort of see. Like if you wanted to do linear algebra with this system, you
Yeah.
could. Right? Is that?
Well, my guess is the idea is that linear algebra is too much a sort of big object. You want something much smaller than
Okay.
linear algebra.
Okay, so you could, but you don't really want to.
So that's my
Yeah.
interpretation.
Yeah, and I've not gone through the exercise of finding out, you know, can this be just straight mapped onto linear algebra, or is other? Okay.
One comment about that is that you can, of course, this R could be a permutation matrix, right? And that's natural for a lot of people in linear algebra. But notice what you have to do there. You have to make 10,000 squared object.
Yes, there you go.
Whereas what you're doing is really just changing the coordinates of 10,000 dimensions.
When you really just
Why do
you're just swapping
shouldn't want to
coordinates.
make,
Yeah.
you don't want to make that
Yeah.
big object. So
Okay, so you can sort of, yeah.
that's why linear algebra is not so useful here, because the object is kind of like impossible to make. So
If you want to do a partial rotation, so like swapping coordinates is tantamount to a 90-degree rotation. And if you want to do just like a partial rotation, then you're going to pay a big price for it, because now you need a full matrix to do that.
You could also get to do some more, what is this, operations equivalent to certain dense matrix multiplies by using fast Fourier transform. Right. So if you do a fast Fourier transform on the vector, then it will multiply, and maybe fast Fourier transform back.
Yeah.
That might be correspond to some dense matrix.
And that's and that's the method that's used. Yeah, used to speed up if your vector, instead of being binary vectors, if your vectors are real vectors, and that's also in Tony Plate's holographic reduced representation.
So are there efficient implementations of each of these operations?
Engineers like this. Yes. XOR is very easy. Thresholded sum is relatively easy. A permutation is just the wiring. If you do certain kinds of permutations are very easy, like rotating. You just move one to the next and then bring around the tape.
In general, the permutation seems to need an iterative mechanism.
Yeah. Of course, the number of possible permutation is huge, but a system may not need very many permutations to be able to be doing something very interesting things.
So you don't mean like let's just think 3 dimensions. If you swapped x and y, that's not a rotation, right? That's a reflection. You couldn't rotate the whole frame to get so it's not necessarily a rotation. It's a rotation reflection.
Some permutations aren't rotation.
Yeah. So have these actually kind of been built like with real 10,000-bit logic gates that do all these things and whatnot? Or
People are working on that.
Okay.
They're research projects.
Okay.
And you may have heard the word of memristor.
Yeah.
Well, memristors, they are programmable resistors, but they are not very exactly programmable, and they are not high resolution. But something like memristors or their relatives are very natural hardware components for building systems of this kind. Yeah. So those just like in ordinary computing, we have several operations. Here we also have the corresponding operations. And then I've already mentioned that you need a separate memory. I mean, these operations are used to do encoding, and then the memory is there, so you have produced some information you can put it away and then use later. And a model of that kind of memory, neural net associative memories. Hopfield net is sort of that kind. Sparse distributed memories of that kind. In general, these are referred to as content addressable, and they are addressed with these high-dimensional vectors, and they store high-dimensional vectors. The address can be noisy, and still you can retrieve, if you store things as point attractors in a neural net memory, then you can probe the memory with a noisy address, and it can retrieve what actually was stored. And the thing is that it is possible to make these kinds of memories arbitrarily large. And arbitrary means is that the theoretical limit is way beyond, it's astronomical. And that's what guarantees that we have memory that would last like a lifetime. So now let's see how information is encoded into these 10,000-bit words, or in general into high-dimensional vectors. I mentioned earlier that the information is distributed, and here, to contrast what I mean by distributed, we take our normal use in the computers where information is not distributed. Like if you have a traditional data record that gives you a variable and their values, here have three variables and their values. In a traditional computation, each of the variables is assigned a certain block of memory, and then you just put the value in a specified area, and so that's where the information is localized. And here I say, okay, now we want to put the same information, the variable x has value a, y has value b, z has value c. We just want to put it all in the same 10,000-bit word. And so next I show how we can use the operations I mentioned here, how we can use these operations to encode this record in a holistic or holographic way.
One comment, because I think it may not be clear to people. When you take that sum, a plus, or go back to the sum, you're taking winner takes all, or whatever, right? That's a majority.
Yeah.
Okay, I just want to make clear that that's not obvious, but that's a majority.
Oh, yeah. Threshold, yeah. And it'll come in the next picture also. But
So, right?
yeah.
Has there been work looking at other vector operations and whether, like, expanding on this list? Like looking at, like, you know, pairs of HD vectors and information about them, like.
Of course, this works on a pair and this works on a pair. The permutation doesn't work on a pair. No.
For example, like a determinant or of like a area occupied by a pair of vectors, or just are there other things and constructs in linear algebra
Yeah.
that they can apply to this? Or?
I would say no, but for different kinds of vectors, the corresponding operation for different kinds, we have corresponding operations for real vectors, we have corresponding operations for complex vectors, but take any single kind of vector, we haven't considered any additional operation. We just deal with addition, multiplication, permutation. And the claim is that, first of all, it's fully general, it is readily implementable, and it produces actually very efficient algorithms. It's sufficient for efficient algorithms.
Just to be sure, add here is in reality in binary vectors is or, right?
That's what I was trying to explain. It's not
No, it's not or. It's not.
Majority.
It's a majority.
two zeros and a 1, it's 0. If two ones and a 0, it's
Yeah.
1.
Oh,
Yeah, it'll come when we go through this example. Also, we'll return to it. But you had a question.
So for the thresholded sum, is that supposed to just have 3 inputs, or?
Well, thresholded sum is a little bit tricky because so long as you have an odd number of inputs, it's clear. I mean, either in any one column, either zeros or ones are more common. If you have an even number, you get ties, and so you have to have some way of breaking ties. And here we just say we've been a little bit casual about it. So you can just break ties at random, and still you get a system that works. Okay, so now we want to see how this particular expression is represented in a 10,000-bit vector. And we start by, we have to have something as seeds for this operation, and for both the variables, for the values, we represent each of those with a random 10,000-bit vector, and these bold-faced letters stand for 10,000, random 10,000-bit vectors. Very, very important to note here that those are random, because once they are random, they work very nicely in this system. And first we saw how should we encode the idea that the variable x has the value a. So here's our random x, and here's our random a. And for binding, for expressing that x has value a, we use the multiplication operator, in this case exclusive OR. So if you look at here, this binary string is the exclusive OR button. You just go coordinate by coordinate, and I just copied it here to the right because it fits in a couple of slides down. And do the same thing. Y has value b. We use the multiplication operator of this system to produce a vector that represents that concept, and similarly that z has value c, it's a vector. And now we want to combine these three variable value pairs, and we first do the addition, and so here we just get zeros, ones, twos, and threes, and then we do a thresholding at half the number of things added together, and so we get a binary vector, and as the result. And as I said, if the number of things that you are adding together is even, you have to have a way of breaking ties, and ties can be broken at random. Okay, Chris?
Does the sparsity of that sum vector sort of hold to the...
In all of these examples, I'm using dense binary vectors. Zeros and ones are equally likely. And what it turns out that when you use the exclusive OR as a multiplication, it retains the density. And when you use this addition operator, it also retains density. So it's a closed, in that way, these operations produce a closed system.
Would you expect the exclusive OR to maintain density if you had sparse vectors? I don't know.
No, if you have sparse vectors, then exclusive OR, the number of ones keeps growing. The exclusive OR takes toward 50% zeros and ones. It always goes in.
So would this system not hold for anything but sort of random or...
Not in its pure form. No. And there's one of the things that we, at this point, we really don't have a very good multiplication operator for sparse vectors. We have it for dense vectors, and that's why I'm using those in this example.
I'm sorry, it's probably a bit off. What do you do for complex vectors for addition?
It can be just vector addition.
And then normalization.
And then you normalize, yeah. And then sometimes you end up with the zero component, and so again you have to break, as it were, you have to break ties. Yeah.
y equals b and z equals c. And those ands make me think that those things should be combined some other way, not additive.
Not
Additive
additive.
is more like an or, right?
Well, a fairly usable system can be built with ands and ors, but it will lack some of the properties. Because neither and nor or is invertible.
So like over the finite field of two elements, it is a,
When you,
it is a,
what do you mean when you threshold and
Yeah.
Well,
XOR is it's addition logic, right? Is that-
I think it really depends on what you want to do.
Yeah.
What are you going to do with this in the end? And if what you want to do in the end is take dot products, be like, is this proposition true? Here's my vector, which
Yeah.
contains all of my information and truths. So I say, is this true? And you get a high dot product. Okay,
Yeah.
cool, it is. And then what is it? What about this other one? So yeah, dot product is large. Yeah, it's true as well. So that's how to naturally. That's why I think they have.
well, I guess that's what I'm getting at.
Yeah.
If you were sort of trying to look at the similarity of this to something else,
Yeah.
because it's the sum,
Mm.
if I only had two elements of this mixture, right?
Yeah.
You would say, well, yeah, it's kind of similar, right? If I only had x equals a and y equals b, then it's kind of similar to all three of them together.
Mhm.
Whereas like the and, I
Yeah.
guess, I guess it depends on how strict what you mean by and there, right? It's just like, because and really means like it's the intersection
And-
of those things, the hard intersection, like,
all these
three of these, or else it's
It
over.
means that all these hold together at the same time.
Yeah.
That's what I mean by this and. And. It doesn't matter in which way you think of, in which order you think about it.
Right.
It just the sum operator has the nice property is that it's independent of order.
Is that really true though? I mean, isn't it not associated in that if you add the first two first, and then you have your thresholding operation?
Yeah, no, this is not pure in the sense that it is not associative. If you have these three vectors, and you first add those two to the thresholding and add that, or if you first add those two and then do the thresholding and add that, you do not get the same result. So we do not have purity, but we have something that is workable, and it.
So what you're saying is that it's not associative exactly,
Yeah,
but if you for the things that you care about, like checking if
it's close enough.
then it's close enough.
Yes.
So when you do the unbinding, regardless of the order in which you bind them,
yeah.
you get sort of high dot products.
That's right, and that okay, and the reason why that is sort of forgiving high dimensionality is the reason. I mean, you just even if in any particular column it just didn't work, but over the 10,000, and you can make it as reliable as you want to by increasing the dimensionality.
That's actually really interesting, Pentti, is that you could do an experiment where you could try to understand how much it's not associated, right? I mean,
Yeah.
right, if you're doing an operation using these techniques, it might be that the outcome of the operation is independent of these choices. And that's what he's kind of saying. What
Yeah.
Pentti's kind of saying is there's all these choices of which one to do first and
Yeah.
so forth. In fact, an exponential number, essentially. And yet, the computation is robust to that because
Yeah.
of the high dimensionality. I think it's a really great project experiment to kind of understand
Yeah.
it.
And I think my thoughts are similar to Hiller's. Like, you could look at multiplying these things or adding them, I guess, in
Yeah.
different orders, right? And
Yeah.
throresholding and seeing like what is the overlap. What's the
Yeah,
top
yeah,
line
right,
between the
right,
results,
yeah.
And it's probably
It turns out the exclusive order doesn't matter in which order you make them because, but it's the addition where yeah.
Yeah,
Okay.
I mean, I think you can do that analytically too.
Yeah.
Because each component's independence. There's only
Yeah.
8 possibilities for each.
So now we have this vector, call it H. So this corresponds to this, and now the next thing is that what can you get out of the vector that has been produced with these two operations, and so we can ask, what is the value of x in this composed vector h? So that's I mean, can we? I mean, if you're dealing with ordinary computer, you just what's the value of x in this record? You just have to know what the address of x is, and you just retrieve it from that field, x field of the record. Now here, since everything is distributed all over, it's not quite that simple, but still, it turns out that it can be recovered. The value of x in that composite, it can be recovered. And then here again, we have the vector for the record, the combination, and then we have the vector for x. And we can use, in this case, we use, again, the multiplication operator exclusive OR. It turns out exclusive OR is its own inverse. In other words, we want to multiply with the inverse operator, but here it's the same, and so we get another vector out. It's not exactly A, but it's close enough to A, and that's again statistically very easily shown that at the very high probability it is approximately A. And if we have an additional system in this, additional component in this system, I call it the item memory or cleanup memory, that includes all the known vectors in the system, then and have a method of finding the closest match among the stored vectors. It turns out the very high probability the closest match to this unbinding operation is the actual value that was encoded into the composite.
And
So
would that cleanup memory just be a dot product with all your known vectors?
you can, yeah, and we leave it as a problem for homework for engineers to figure out how to do that efficiently. Yeah.
One other question. Do you consider the not operation, and would that be useful in this system?
Not it's I'm in my examples here. I'm not using it, but yes, the not really what it is that you take the complement and you add a complement, and that in other words, it's not produces a complement. If you add it into a sum vector, you can remove an element from a set.
Right, yeah.
I mean, this H is a set of 3 bound pairs, and you can remove one of those 3 pairs using the first or not, and then at that and that's again, it's a fairly simple geometric argument that shows that you can. That's true. I didn't have a complement as one of the operations, but it's easy. You just you exclusive OR with all of ones, and then you get the complement. Now, if I address all of the above in symbols, then the vector H, that is the holographic record, it's the sum of 3 bound pairs. And then if we ask what's the value of x in H, we did multiplied H with the inverse of x. And now here's something very important. And the important thing is that, okay, so here I've just written down what this means. The important thing is that the exclusive OR, it distributes over addition. And it distributes exactly if the number of things that you have added is odd. And so this is actually equality. The exclusive OR can be worked into that. This is something very familiar to us from just ordinary math, is that multiplication distributes over addition. Here just somewhat more general, in a somewhat more general setting. And so now, since X is its own inverse with exclusive OR, that yields A, the vector A, and these two other exclusive ORs, they are noise in a sense that they don't resemble anything that the system has encountered so far. So that's why we say that's approximately A, and the reasons are, okay, the multiplication distributes over addition, and this time the multiplication cancels itself, and the noise simply means that there's nothing similar to those vectors in systems experience. Bruno?
Pentti, did you say that the number of elements in that sum has to be odd? Is that what you said?
It has to be odd because if you add an even number if you have an even number, then you have this slight ambiguity of how you break ties. The tie breaking in both cases you have to break ties when you produce a sum, or then when you multiply with X you have to break ties, and if you don't break them in the same place, then you get again just approximate result. But so this is either exact or approximate.
I see.
Yeah, yeah. And that's just the fact that you do not have a majority. You do not guarantee a majority. I mean, in a majority of places, you can determine what the majority is. But occasionally you have ties. So we have used these operations. Okay, first of all, now, so that was how you can actually put information into a vector and then extract information from it. And we have used, one of the examples we have used these operations in is example of recognizing languages. And there the initial impetus is that we can recognize languages even if we don't know them, by just having heard, okay, this sounds like Russian, this sounds like Chinese, this sounds like Spanish. And so we're doing a similar thing here, but instead of using the sound and voice, we just use letters. We use text in this experiment. So we could say, instead of how different languages sound, what do they look like when printed? And the way this experiment was done, it was done by two of Bruno's students here. That's a class project. For each language, we take a bunch of text. I think it was about 1 million bytes worth of text in 21 different languages. And for each language, we just computed a 10,000 dimensional profile. And the profile summarizes in this case, it summarized short letter sequences. And in the examples I show, some trigrams, all the trigrams that were in a text with which the profile was computed. And this kind of profile, it is a form of histogram, and you can actually turn the profile into an approximate histogram. We will not go, or histogram, you can turn a histogram into a profile with these things. So how is this done? How did we produce profiles for languages that were used to recognize languages? And it starts with providing random seed vectors, and since we're dealing with written text, we just used a random vector for each of the letters of the alphabet, and then the space character. So there were 27 random vectors used as representatives of the alphabet. And then to encode a 3-letter sequence, a trigram, we used the former permutation, which was simply just rotating. And if you take the trigram THE, the vector for T was rotated twice, vector for A rotated once, vector for E was taken as such. Rotation means that you take the bit and put it there, and then you add the 10,000 bit vectors. So in this case, instead of bits, we just used vectors of ones and minus ones, which is equivalent. It's called bipolar, but it's equivalent to binary system. And if you use this ordinary multiplication, it's equivalent to the XOR. So this is just a very simple way of using ordinary arithmetic operations in the computer to produce a vector for each of the trigrams in each of the text samples that we dealt with. And if you translate that into symbols, the trigram THE, the T is permuted twice, the H is permuted once, E is not taken as such, and then you just multiply the resulting vectors component-wise, and then one of the very important properties that this kind of multiplication provides is that the vector that is thus produced for the trigram it's approximately orthogonal to all the letter vectors and to all other trigram vectors and to all possible tetragram vectors, which means that when you're dealing with orthogonal vectors, they sort of retain their identity even if you pile them together like using addition. It means that you can identify individual things from the sum of a very, very many vectors. Okay, so that was for each trigram, and then we just add all the trigrams. And so if we have a text like this, the quick brown fox, it provides these trigrams, space TH, THE, HE space. And so if you have a million bytes of text, million characters of text, your profile will be the sum of a million 10,000 bit vectors, each of those vectors standing for a trigram. And that's
Here are the sum in conventional states.
That sum is the arithmetic sum. Now we're dealing with the arithmetic sum, yeah. It can, if you accumulate the arithmetic sum and then just turn it into binary by just what the sign is in each position, you still get a quite recognizable vector that can be used to identify.
Before you used arithmetic sum with a threshold, like above 0 you put 1, below 0 you put.
Yeah, and here too. I mean, you produce a sum vector, which is sort of a sum of million 10,000, and then at the end you can either use that to compare to others, in which case you would use cosine, or you can binarize it and then use Hamming distances. If you binarize it, of course you lose some information, but you retain enough information to be able to do very accurate discrimination, so long as the dimensionality is high enough. And so when we had done all of this, then we can compare, we can produce these high-dimensional vectors for each of the known languages, and then take a test sentence and produce, using the same algorithm, produce a corresponding vector for that, and then compare, what is it closest to in among the language vectors that we have accumulated, and we can use the cosine measure in this case. And the cosine has a nice properties: 1 if the vectors align, and -1 if they are opposite, and 0 if they are orthogonal. And this is what happened when we clustered the language vectors. There were 21 language vectors. They were from European language corpus. The clustering actually corresponds very nicely to language families. Here are some Slavic languages clustered together, and here are these are Baltic languages, Greek. I guess it's just had to be someplace. Scandinavian languages. English is sort of a little bit like French and a little bit like everything, and then of course the Romance languages. So that when you get clustering like that, you sort of believe that this method of computing profiles actually captures something about the nature of these different languages, and so it in some sense it corresponds to, I've heard different languages. That sounds like Russian. That sounds like Chinese. I don't know either of those, but they just sound different. And so this kind of algorithm could be sort of used to understand how just having experience, having something, it produces a trace or profile that allows things to be identified later or grouped later. Okay, and then
just
yeah.
one question. I don't know exactly how you do this, but would you get similar results if you compared the trigram histograms of the different languages? Like,
yeah.
you just
if you actually do the histograms, we get, of course, if you do the actual histograms, you don't lose any information. Here we have compiled information, so it's all the information is in the histogram.
So it's kind of like a random projection of that.
And if you use
There's so many trigrams, 3 to the power of what? 9?
yeah, but you can have a histogram of trigrams also.
Power of 3.
Not histogram of letters, but you can have a histogram of trigrams. And then compare the.
There's 27 to the 3 trigrams.
Yeah.
It's not that bad.
Yeah, not the back.
There.
27,000.
You don't
Yeah.
have to enumerate all of them here.
Yeah, that's the benefit.
Yeah, and if instead of trigrams, you tetragrams. Of course, in million bytes of text, you will hardly get all of those tetragrams.
Well, I thought there was some question I thought you were asking, Alex, is if you did the brute force
Yeah.
approach, let's say you did that, you collected the entire histogram
Yes.
of brute force.
Which we have done.
How much? Oh, you have done.
We have done it with this.
Oh, with
Not with tetragrams. With trigrams, you have to be prepared to store this many.
You have to
You need to be prepared to store this many different numbers.
You went ahead and did that. How much better do you do? Than
Somewhat better.
you do.
Somewhat better. I mean,
A teeny bit, or
not enough better to go worth the trouble.
it doesn't warrant. It doesn't
Yeah.
warrant all the trouble you went to.
Yeah, that's what we conclude.
What you're doing is really storing histogram approximately.
Yes.
Yeah.
Right.
And if you have the actual histogram of all the trigrams, you can turn that with a simple linear operation into the profile, 10,000 dimensional profile. I mean, that's just the linear. Yeah, you need a matrix that has 19,000 by this squared matrix. What we're doing here is that by projecting things into high-dimensional space, but then operating in a high-dimensional space, we no longer need to increase the dimensionality of the space to capture most of the data, because most of the data isn't there anyway. As I said, in a million bytes of text, you will get only a very small fraction of the possible tetragrams.
Most of those will have count 0.
Yeah. So things get very sparse. When the number of possible alternatives is very large, and so that was my previous picture was just how those vectors sort of distributed in space, and now the next one was we just took single sentences, and there were 21 languages. There were 1,000 sentences of each, just one sentence, and then computed the profile for that sentence, and then compared to the 21 profiles for the known languages, and that produced about 97.3% correct identification. And if you take the second best, it usually was in the same language family. So that again shows that this method of computing profiles produces fairly usable profiles. And then another thing which should be noted, that going through this computation, it really wasn't. It took less than 8 minutes to train on 21 languages, each one with about 1 million bytes, and then test 20. The resulting algorithms are very simple and very, very fast.
How long would it have taken you to collect the histogram?
Probably the same.
Oh, really?
Probably the same, but then
there would be an extra price for that, because with the histogram now, for every trigram you get,
yeah,
you have to look up.
Yeah, you probably use some sort of hashing.
Oh, never mind. Okay.
Some sort of hashing would allow you, and hashing and what I've been doing, they're sort of related things. Yeah. Anyway, we're just hashing, but we're hashing in a dissonant way with operators.
And for quadruplets, it performed worse. Why do you present? Why do you present trigrams results and not tetragrams?
Tetragrams actually performed a little bit better. Why did? That's a simple reason. This was easier. I didn't want to include an extra line there. Okay. I mean, it's just.
That's a brilliant contribution.
Yeah, it's yeah, and the result was much, and also it just makes somehow it makes clear presentation.
Yeah, because for tetragrams, I think it's just impossible to do on normal computers, right?
Well, then you really have to use some sort of hashing method to tabulate them. Yeah, that's true. And now here's the page for. Well, this is for Chris and other algebraists in here. What kind of things about these operators really are important? What come to play? What matters? First of all, is that a randomly chosen vector is dissimilar or is nearly orthogonal to. Okay, now when I say randomly chosen vector, easiest for you to think is the vectors of ones and minus ones, where the ones and minus ones are equally probable, because those are kinds of vectors we are probably most comfortable with. And also, it's a zero mean, and so the orthogonality of two such vectors is very simple. You just take the dot product. If it is zero, the two are orthogonal. You don't have to worry about thresholds or anything. So anyway, if you take a randomly chosen vector of this kind, it is with two such vectors, they have very high probability they are nearly orthogonal. The dot product is very close to zero. And then, but when you add such vectors, the sum vector is similar to whatever went into the sum, but both multiplication and random permutation produce a vector that is dissimilar. And again, so it's multiplication and permutation, then they are, in some sense, they can be used as randomizing operations. You have something you want to randomize it, you multiply it, or you want to randomize it, realize there's anything so far, you either multiply with the appropriate vector or permute. And here's another very important thing is that multiplication is invertible and it distributes over addition. And that's very easily seen with the numbers ones and minus ones, vectors ones and minus ones. Also, permutation is invertible and it distributes. In this case, it distributes over both addition and multiplication. So now you have invertible operation that can, in some sense, it can work itself way into a sum of products, which means that you can unravel, if you have a distributive invertible operations, you can unravel what into the composition. And another thing is that both multiplication and permutation preserve similarity, which means that if you take two vectors that are this far apart in the original space, when you multiply them, they're still the same distance apart. Or if you permute them, they're still the same distance apart. And all of these things actually come to play in the example that I showed about the languages. So all of these terms I've used here, they come from algebra, abstract algebra, modern algebra, and so I feel that the mathematics of this next generation of computers is really abstract algebra. And abstract algebra, when I was studying and I took some courses in math, abstract algebra seemed the most useless thing ever. So have I learned my lesson?
As opposed to, I guess, so the abstract algebra as opposed to Boolean algebra.
As opposed to Boolean algebra.
Currently it's all based on Boolean algebra. So what you're saying is the next generation of computers is going to get smarter computers.
And I think that is the right terminology to use, and provides the concepts.
What distinguishes abstract algebra from just like Boolean algebra versus just algebra? Well, no, it's like this. Like Boolean algebra is a type of algebra.
Yeah.
Okay, that's like it satisfies all the axioms, and then you can go with it. But algebra in general is just a set of axioms and like general properties of those. But which gets really exciting is when you pick a specific field like this one or Boolean algebra, and then you start understanding properties through the lens of this framework. That's the benefit it's provided.
So what makes it abstract algebra?
Well, because typically when people think about algebra, they think about like real numbers, adding and subtracting, and multiplying. These can be anything in a set, like a bunch of doorknobs. I mean, whatever. As long as you have some way of combining them in these ways that we call algebraic.
That's the abstraction.
So that's
Something beyond numbers. In this case, the abstraction is two vectors.
Yeah, the vector. Yeah, and the interesting thing is that whether the vectors are binary or real or complex or something that I don't even know, haven't heard of yet, you still want to talk of the addition operator and a multiplication operator in that algebra, and an inverse operator, and a distributivity, and similarity, and preserving similarity. Those concepts still come to play, and so the abstract part, I guess, it means that it just is more general. And in some sense, I said abstract algebra is the mathematics of mathematics.
There are more than 200 algebraic systems, in
Yeah.
study currently. So sometimes it's a little bit to justify that a specific algebraic system is worth the most. I mean, for example, Boolean algebra, I guess the justification for that is we have the gates, right? So we have the binary gates for that. So maybe it really depends on what devices we have in order to determine what algebraic system maybe we want to study.
And I'm sorry, one more question about you're saying permutation is now distributes over multiplication and addition. So is the way to sort of read that is that that means permutation of A times permutation of B equals permutation of A times B?
Yeah.
So I guess in that sense, maybe this sort of contradicts what I was thinking earlier, because I was sort of wanting to equate permutation with like matrix multiply, but that wouldn't be the case with matrix multiply, right? Because if you had matrix times A times matrix times B, that would be something like
that
times A times B.
generally probably wouldn't be. Yeah.
Right, so is that, okay.
Yeah. And here it's because you're just dealing with individual coordinates. So that's the condensation of math. So I've talked about this. That the good terms to think about this is in algebra terms. And if you look at what algebraists call these kinds of things, the algebra numbers they produce a field. The addition and multiplication operator produce a field. In this system that I have shown, they constitute an algebraic system that's approximately a field, but it's close enough so that if you found some good uses for a field, they probably hold in this system as well. And then we have this added operator. So over the field, we have an added operator, which you would expect that it would give some additional power to this system. And one of the things is that something that we haven't really looked into at all, you can implement any finite group as a permutation. And so there's rich math yet to be explored, and what if you mind sort of this vein, I don't know yet.
Well, let me just say another way. Any finite group is a subgroup of a permutation group. Yeah. So if you want to know, so here's another way to say it. You look at permutation groups and all their subsets, you will find every group. Every subgroup of permutation group, as you run over all permutation groups, will hit every finite group. It's kind of crazy. So it means that permutation groups hold everything. You see what I'm saying? Like inside of a permutation group is every group.
Yeah. And then having an algebraic system at which you build structure, it means that you have some hope of actually analyzing and producing a computational system that is transparent instead of a black box or black magic box. Yeah.
Could you talk a bit more about what you mean by approximate a field? What property of a field does it?
Okay, it's like the addition. If you remember the binary, the addition it wasn't exactly associative. It's approximately associative.
Okay.
Yeah.
Well, so I guess you don't have 0 and 1 here, right?
Yeah. And if you take a vector ones and minus ones, you don't have a true 0 in that.
Right.
in that, if it's just ones and minus ones, you don't have a true zero. You have a true one, but you don't have a true zero.
Oh, you don't really, right? You don't have true one because you limit yourself for 50% probability.
Oh, okay. Yeah, okay. Yeah. So that's what I mean. Approximate. It's, you can expect some of the properties of field to hold approximately. But field is basically it is sort of inherits the things that you get with the field. Yeah. So
every time I hear this word,
yeah.
I think of like electromagnetic field or something. So I mean,
Oh, that field.
Why is it called a field? Or what is that? How do you think of that? I mean,
Okay, well, I don't know. Maybe they had used group and they had used ring, and then what word can we use next?
What a field is a ring which has every element has an inverse.
Yeah, but the ring is, yeah. This
ring
is
what you think. It's a set with a abelian group under an addition, and a distributed multiplication.
yeah.
So it's kind of a system.
Yeah, group.
Axioms,
Yeah.
and it's a collection of axioms and a set that satisfies them. That's a ring. Specific ring. And then now if you add the extra property where every non-zero element has an inverse, okay, that's a field. Let me give you an example. So the integers under addition is a ring. Why? There is an addition that's commutative underlying everything. There's also a multiplication that distributes. Okay? But it's not a field. Why is Z not a field? The integer not a field is because not every number has an inverse. In fact, none of them do, except for like one.
Yeah.
So,
One has an inverse.
So now if I take, let's expand it a little bit. Let's make fractions then. So rational numbers. Guess what? Rational numbers are a field. Okay? That's the kind of thing we're talking about. So ring is an object that is very general, like integers, and then if you add a little more like inverses, then you get rational. That's the kind of that's a field is
that helps a lot. So
Yeah. And then
is there a reason that? So why is it called a ring and why is it called a field? Does it matter, or are we just supposed to memorize that? I mean, is there?
Well, it matters because mathematicians call it that.
I know.
Yeah.
I mean,
This-
Physical interpretation.
it's just something.
This is one of the things I have a similar problem with the vector, because when I use vector, I think of numbers, but when pathologists use vector, it is something that transmits viruses, and when so it's just the nature of language that you sort of have to be in your own field and those.
Viruses are just a string of bits. In that way.
Yeah.
I guess the viral vector is the end.
Yeah. Virus is a string of. That's another thing. Yeah. Another thing, like group, has only one operation. That's what's called multiplication. Both ring and field have two operations, and so all of these are closed in the sense that when you produce the operation, you end up in the same base set. But in one case you have one operation, in the other two cases you have two operations. So, and then when you have two operations and they interact in a nice way, then you can take a sum of products and you can break that into individual. Yeah.
So is there a mathematical expression that has permutation? I mean, so like because you say that like just plus and multiply is a field, but
Group is like the lowest level.
is there something that has this extra flexibility that's
It's like an additional operation on
Yeah.
on individual things, right? And I guess you just add that in as like, here's another unary operation, right? That has certain properties, and then you can investigate that.
Okay, well,
I'm sorry. Go ahead.
and what I said already, high dimensionality is the key, because in high dimensions you have a huge number of nearly orthogonal vectors, and randomly chosen vector is nearly orthogonal to anything you've seen so far in a human lifetime. And here just how it goes with 10,000 dimensions. If we compare the central tendency of in this case, the binomial distribution when the n is 15, then you get this very broad distribution. When 10 is 10,000, you have hardly anything that is close, hardly anything. You get halfway into the space, nearly everything in that space is about halfway into the maximum distance. So that's to get the summary slide. This kind of computing is based on very rich and it's often subtle mathematics of high-dimensional spaces, and it's not. I don't think it is subsumed under linear algebra. And the high dimensionality is more important than the nature of the dimensions. So these proper operations exist. I mean, are known for real complex vectors, and this holographic or holistic distributed representation makes this kind of computing very robust and also positively brain-like. And here are some early characters who have been working in this area. I'd say Tony Plate and his holographic reduced representation in some sense started this field, and probably the most best known in the world is Elias Smith's semantic pointer architecture, except that he doesn't explain it in terms of semantic pointers as much as in terms of spiking neurons. And would make the following forecast. This computers of this kind that exploit the high-dimensional geometry they will be built in our lifetime, and they result in simpler, faster, and more powerful machine learning algorithms that could be used in something like natural language, analogical reasoning, vision, multi-sensor integration, big data. And in general, it's kind of open-ended. And one of the things about the open-endedness is that if you need a new entity, you just need a new random vector, and it fits with whatever has been done before because it doesn't interfere very, very seriously with things that have been included in the system so far. And this high-dimensional computing, it is very well suited for the new nanometer electronic technology. People talk of building computers that would be sort of comparable to brain in terms of their connections. Now, this may be the right theory according to which such computers would be built. In the meantime, we need to sort of learn to use this kind of computing and operations and machine learning algorithms, and our present-day computers are more than sufficient for not just experiments, but also for practical applications. And here are some sources that have funded our work. And then I thank you all, and maybe it's time to go to lunch, but who wants to hang around? I'll be here. Thank you very much.
Just one other question I have about the field is, I've heard you say this many times, why are we so excited about that? Why is that such a fundamental property for building a computer?
I would say, for me, it's because the way the operations sort of work with each other, distributivity, inverses, and certain operation preserving similarity, other operations producing similar result. they provide a means of analyzing what's going on underneath. I mean, I think the real problem with some of the deep learning things that we do now is that we have no good way of sort of looking into it, because the operations, they are not well understood. The operations that produce the internal representations are not well understood. Here, the operations that produce the representation, they are well defined ahead of time. We know how the operations.
Yeah, but it sounds like then there's two different distinctions to deep learning. One is the ability to have interpretability,
Yeah.
transparency, right? Understand what you're doing and all that stuff, right? But it seems like there's another thing, which is like you're saying that linear algebra is not subsumed under this HD computing family of things, right? Which would mean that neural nets are not subsumed under potentially, right? So
Didn't you say the opposite though, that this is not subsumed under linear algebra? I think.
Yeah, I believe that it is not subsumed under linear algebra.
Well, linear algebra may or may not be subsumed under this. Is something
may or may not. Yeah.
Oh,
Yeah.
Everything is just like you want to have basically two operations. You want the similarity operation, and then you want this sort of dissimilarity operation that throws you into another part of the space, right? And then you think, okay, well, these two operations also have to play a certain way together to do what we want them to do. And what's a mathematical object that we already know about that has two operations that play together? That's a field, and that's where the analogy comes in. But it doesn't have to be, a field in the strict sense. But I mean, that's the analogy that you drawn here.
okay, cool.
It's
But I guess what then what are we then?
Yeah.
Are neural networks a field? And if not, then it seems like that's the point of distinction. You're saying potentially there's a sort of fundamentally different class of computational system than neural networks. Would that be another thing you
Yeah. Maybe I can answer it with your help, and that is.
What do you mean by neural networks?
Yeah. Yeah. No. Okay. In all this system.
Well, I know they don't preserve dimensionality to begin with.
Yeah.
Think of linear algebra as like I just get to add and maybe multiply by a scalar. Okay, that's it.
So.
And here, when I get to deal with multiply vectors, that's a new thing. I can do something now. Something new, a new mixing of things, and that's it.
One way.
You could define one, maybe. You could define a field out of neural networks.
Yeah, right.
One way I think that there's a base set, and in this case it's this high dimensional vector, and there's operations that take you back in the same set, and so now you have produced representation for a pair, and you can use the same operations to build a bigger structure that uses that as, and your dimensionality, everything always stays the same. You always stay in the same mathematical space. The operations don't take you like if Smolensky's binding, he uses vector product, and so the dimensionality at every step, the dimensionality keeps increasing, and so it is not closed. That system is not closed under its operations. It just yeah.
Unless you include all of them in the set.
All of the expansion.
Yeah, exactly. And then you can start talking with.
Is Boolean algebra a field?
No.
What do you mean Boolean algebra?
What do you mean by that?
Common
Well, I mean,
and or?
Do you need a field to do computation?
No, you can. A field is a kind of algebra.
Inverting
right?
is very
It's
key.
a kind of algebra.
Yeah.
Inverting is the key.
Yeah. In Boolean, and and or don't have inverses. They are not invertible. They and or distribute. So distributed is fine, but you don't have the invertibility. Whereas the multiplication is invertible.
One other thing I sometimes think about this, is the idea of like a key value store. So you have an object that stores like values associated with pointers, and so you can like probe your system. So that's like a common thing in like in Python you'd have a dictionary, or you might call the hash table or something. So it's like implementing a key value store
Yeah.
with a finite dimensional, or like a fixed number of units or something like that. I guess you have to store the keys and the values, or the keys also.
Yeah.
It's even more general than that. I mean, you have a tree.
Right.
By a particular choice of the vectors, and like you have powers of multiplicative powers of those. You could have like multi-dimensional lattices, I think pretty much any kind of data structure.
It's like any graph that has, you have a sequence of keys and then you get a value at the end or something like that.
And in ordinary programming, you have to have the addresses of locations. They just are part of the instructions, so we don't think of them. But you have to have all that stuff somewhere stored so that you can retrieve it. In this case, we just think that there's this one, in some sense, a symbol table of high-dimensional vectors that are defined in the system at that particular point of time, and you want to find out if what you produce now is one of those vectors or if it's not.
Yeah, so possibly like kind of silly, ridiculous question, but so basically, as far as I understand, this sort of 10,000 dimensional vector over Z2 is basically giving us something that's sort of kind of like just the finite field of 2 to the 10,000, right? So there are like people who do care about finite field and information processing, right? Those algebraic coding theory people that give us like Reed-Solomon codes.
Oh yeah.
So is there kind of like, is there sort of a connection to that community of research at all, or has this kind of just been going in a different direction and not really?
I think this has been sort of in different circles. This has been developed in cognitive science mainly, and the other cognitive science and computer science. Well, I don't think they know what the other people are doing. One group knows very well what the others are doing. So that's. But definitely, I think there are many points, possible connections.
Right.
When you go in a high-dimensional,
things like doing efficient operations on these finite fields, are things that like people in those algebraic coding theory circles have been doing for like 40 years.
Oh yeah, right. So, yeah, those are the right people to get sort of looking into this. Yeah, and that's right. You're right.
At the beginning, you motivated a lot of talking about this by talking about brains.
Yeah.
Is that sort of like artificial neural nets where you're like, hey, there's kind of layers and neurons, and then you go off and do stuff?
Yeah.
Or do you imagine there being like this, like coming around in a circle where they have these high-dimensional representations of particular schemes you use to do the math back onto biology in some way?
At this, I think of this as a new just field of computing, or sort of extension in the field of computing. But it may, over time, show, okay, well, this particular algorithm within this particular setup seems to behave very much like human memory, a perception of something. I think there will eventually be some feedback into biology as well. It's
Well, that's why actually when I made my comment I made earlier, that this has artificial neural nets, like these neural nets are not, I don't think they're biological at all. This I think it has a much has this, like he mentioned, there's this various cognitive kind of similarities, so like memory accuracy, but that fundamental property where it's like, okay, we're going to recognize from the start that everything's random, and we're going to leverage this stochastic nature of this thing, gives it this property that is super distributed, and you can hack away at the system and it still works, but you can still do really interesting computations. And I think that's I'm not personally aware of any other framework that addresses that problem as directly. And that's something that's like a really high level of constraint that the brain ought to have, but I don't think we really understand computing in general in that under that constraint.
What's the
constraint? Like,
Being able to tolerate random damage.
I had another question. Is there like a more formal definition of like distributed representation, or like what do people say about that? Or is there, because that's that term's used a lot.
It's a somewhat loosely used term.
Yeah.
Yeah. And
In terms of Eric's question about mapping onto biology a little bit more, one example, so in Pentti's book on sparse distributed memory, there's a pretty compelling chapter on sort of mapping some of the ideas, which are a precursor to some of the algebraic ideas here, onto a particular part of the hippocampus.
not
And then
hippocampus. Cerebellum.
The cerebellum.
Cerebellum, yeah.
And then this name of this holographic thing comes from holography, which I think maybe Marr and some other people had some other analogies they were making to specific parts of the brain, some of these kind of structures. So I think there is a little bit of prior work on that.
It's almost like you have to deconstruct everything you've been told about neural networks to sort of reformulate a theory of brain function in terms of this way of thinking. But when you do, to me, it actually
more natural, right?
It's much better. And then you sort of realize post-hoc, after the fact, that the reason why we sort of went down this road of modeling single neurons, single neuron view, is kind of because of technology. You just had electrodes that could record from single neurons, and then you could record from this neuron. You say, well, that neuron does X, and this neuron does Y, and then you come up with a story that the brain works that way. But it's one thing. Historical notice worth mentioning is that one of the things that made Hubel and Wiesel's finding, and also the work of Kufler and Barlow, and this happened in the late 1950s, and what the frog's eye tells the frog's brain. The reason why that work was so explosive and revolutionary at the time is because it went against the thinking of that time, which is that everything in the brain is distributed. It's more holographic. So that the idea that you can poke your electrode into the cortex and you find a neuron that codes, not only orientation but that point in space, is very specific, like a feature detector. It's just like that was just totally anathema to the way people thought about the system. And so to me, it's kind of ironic. It's like for Sokol, it was kind of a distraction. That whole 50 years of people using it. And sort of now we can kind of sort of view it from a more kind of intellectual, mature point of view, and say, okay, well, it's not wrong. Everything is correct about the results, but maybe there's a sort of different context.
Yeah, and also at the time of Hubel and Wiesel, I don't think the mathematics was readily available for the people who were working on this.
Well, they had filters, right? I think that filters, feature detection, that was very much in engineering. So that fit like a glove.
Had von Neumann lived, his computer in the brain probably would have produced what we produced 30, 40 years later.
Eric's comment about actually trying to find insensitive, sort of robustness against random error. That's another connection to coding theory. That's exactly what polynomial codes or finite fields do. You try to build codes that are robust to random error. I mean, the sort of overlap between these fields, it might just sort of be kind of weird coincidence, but interesting research direction to look into.
Oh yeah.
Coding theory.
Are you in coding theory yourself?
No, not really. I just read a book on it.
Yeah.
It's just lots of things lining up here.
Well, I think what you're observing is a little bit ridiculous. It's like error-correcting codes have nothing to do with polynomial algebra over finite fields, right? Except every single code that you guys have, the little random dots, that's Reed Solomon, is algebra over finite fields, which is insane. Why is that? Well, there you go. Math is powerful. So algebra is powerful, and so maybe the fact that Reed Solomon is essentially the best you can do, and it involves polynomial algebra over finite fields. Maybe this is interesting, right? I mean, so I think that's what you're trying to get.
Okay. Well, shall we just thank you? and we can continue in the hallway.